Good day from Chem Help ASAP. In this video, we'll convert an anhydride into a functional group called an imide. Imides are not a typical acid derivative for college organic chemistry courses, but they are in fact examples of acid derivatives. We will provide some brief background about these functional groups, present the reaction, perform the experiment, isolate the crude product, and characterize the final material. An interesting aspect of this reaction is that the final product is the active ingredient for an approved drug called TPOXX, which is a treatment for smallpox infections. Handouts for the lab procedure and NMR spectra are available through links in the video description. The focus of the reaction in this video is conversion of one acid derivative to another. On the screen, we have examples of many of the most common acid derivative functional groups. All acid derivatives include a carbon atom that has 3 bonds to a more electronegative atom. Very often, acid derivatives include a carbon as part of a carbonyl, and then a single bond to an additional electronegative atom. That would cover carboxylic acids, the parent of the acid derivatives, acid chlorides, esters, anhydrides, and amides. Some acid derivatives without carbonyls include nitriles, orthoesters, and amidines. Reactions that involve interconversion of one acid derivative to another, especially with the carbonyl-based acid derivatives, are a mainstay topic in college organic chemistry classes. This lab experiment involves an acid derivative interconversion and reacts an NH2 group with an anhydride. Typically, anhydrides react with NH2 groups to form an amide. The second carbonyl of the anhydride is lost as a carboxylic acid. If the anhydride is a cyclic anhydride, then it is possible to have the NH2 react not just on one, but both carbonyl groups in multiple steps to form a new acid derivative called an imide. An imide is the nitrogen version of an anhydride. An anhydride has 2 carbonyls attached to 1 oxygen. An imide has 2 carbonyls attached to 1 nitrogen. The experiment in this video involves formation of a cyclic imide from a cyclic anhydride. Finally, here is our reaction. The procedure I am following for this reaction has been adapted from the reference at the bottom of the slide. The structure on the left is an anhydride. It may be difficult to see the anhydride within this complex structure, but the cyclic anhydride is in the lower right corner of the molecule. While the key functional group in this structure is an anhydride, I will frequently refer to this structure as the cycloadduct during the experimental procedure. The reason I call it the cycloadduct is because this molecule is prepared through a cycloaddition reaction, and I have posted a lab experiment video for the preparation of this starter material. We will react the anhydride, the cycloadduct, with this NH2 group, which is actually part of yet another acid derivative called a hydrazide. Heating these 2 compounds together in ethanol forms a cyclic imide. This imide, which has a special name, tecovirimat, is notable because it is the active pharmaceutical ingredient in the antiviral drug TPOXX. TPOXX is a treatment for smallpox. We will talk about the pharmaceutical aspects of the product after the synthesis part of the video. Alright, let's get started with this reaction by weighing out some of our reagents. So I'm going to begin with the cycloadduct. I want to make sure I use a little bit extra of the cycloadduct. Now I know the cycloadduct is precious, but I would rather deal with having excess cycloadduct than the hydrazide. Okay, so here I have on this piece of weighing paper a decent amount of the cycloadduct. And I'm going to go for about 1 millimole of the cycloadduct. That's about 190 milligrams. And so let's just see what we can get here. That's about 80. And this won't be exact, so I say about 1 millimole because that's what it's going to be. So I know there's riveting things here. Okay, that's 170, 180. Let's go a touch over because I said I want to go over. Okay, I'm being all delicate here. That's fine. That is 196 milligrams. Since I've forgotten this kind of thing, let's write that down. 196 mgs of the cycloaddict. And let's put that aside. Looks very nice. We'll leave it right there. Try not to spill it everywhere. And let's get now another weighing paper. So I've gone just a touch over 1 millimole of the cycloaddict, and I want about 1 millimole of the hydrazide. So this is the hydrazide, and I know 1 millimole is 204.15 milligrams. So let's see what we can do here. If I go a touch over, that's okay. So that's up to, that's 114 mgs. You can see that has these little pieces, and they're pretty dense. Again, we're going for 204 or maybe less. Just under is fine. Oh, yeah, you just get greedy. Okay, that is 198 mgs. I think I'm going to stick with that. So that is just a hair under a millimole of our hydrazide, and we were a hair over for our cycloaddict. That's good. We want a little more of this than that for in terms of purification and isolation. Okay, so that's it. So let's take these into the hood and get started. Wonderful. Now we are in the hood and we're ready to begin actually setting up the reaction. So the key reaction flask is going to be this 20 milliliter scintillation vial, and it has a really small stir bar in it. And to that vial, we are going to add the hydrazide that has been weighed out. And I have it off camera, so let's bring it in here. So that's 190 some milligrams of our hydrazide. And to start this reaction, we want to dissolve that hydrazide in a little bit of ethanol. And I want about 3 milliliters of absolute ethanol. This does not need to be exact. Just a small amount of solvent to get everything in solution. And carefully. It's not the best pouring bottle. Okay, that's a little over, but I'm not worried about that a bit. That's really probably about 3.5 milliliters. Not an issue. Pour this in. Good. Now our goal is to get this to dissolve. In my experience, this takes a little work to get dissolved. It's not that it's not soluble, it's just that it's kind of slow to dissolve. So I'm going to go ahead and add one of our other reagents, the Unix base. This is N-ethyl diisopropylamine. Honestly, I kind of question whether this is even necessary for the reaction, but this is what the procedure says to use. I don't want to reinvent the wheel, I just want to get some product, so I will add a drop of that to the reaction vial. And now I'm going to cap it, but I'm not going to really tighten the threads, just engage the threads. Swirl this around a little bit. And now I'm going to place it on the hot plate. Now this hot plate is set up for about 120 degree sand bath. This is what I want for the reaction, but I don't want to start the reaction because I haven't combined everything. So I just want this to gently heat. So I'm just going to place it on top of the sand. That'll get a little warmth. That warmth will help everything dissolve. And then once everything is dissolved, we will add our anhydride to this mixture, and then we'll actually sink it into the sand so we get the full effect of the heat. But I don't want to cook this yet. I just want it to gently warm, and so we'll just place it on top of the surface of the sand bath, and that should be more than adequate to get dissolving. So let's wait a couple minutes, let this dissolve, and then we'll add our last reagent, the anhydride. This is cycloaddict from a previous reaction, and we will get this reaction started. It's now been just a few minutes and everything in here is dissolved. This is a nice homogeneous solution. So I'm going to, let's open this up. And that's just barely above room temperature, just very gently warmed. Now I'm going to take the cycloaddict that we weighed out. Add that in, that looks good. Now that's in the mixture. Gently cap, let's get that stirring, let that mix in. And again, these threads are engaged, but they're not clamped down. And now let's burrow this down into the sand. This ought to be about the temperature of boiling ethanol, which is around 80 or so degrees Celsius. The sand bath is at 120, so the sand bath is a little bit warmer than our desired boiling point. But this is now going to stir at higher temperature, and we'll come back. It's supposed to go 4 hours. We'll come back in a bit and see how it's doing. All right, this has now been going for 4 hours. And I pull this out. It looks very much the same. It's just been heating that ethanol solution. And now I'm just going to put that on the side. We'll let that cool down, and then we'll continue working this up and getting that product isolated. The reaction has now, actually, it's certainly cool. It's been allowed to stand overnight, and there's really no change. There's a little sand sticking to the side, but there's no change. So our hot plate is now cool, so let's get rid of the sand bath. And let's put an ice bath on here. And I'm going to sink this down into this ice to the bottom and let that cool a little bit. And once it's cool, we'll go ahead and take some more steps. In theory, this could precipitate out as it cools, but I don't think it's going to happen. So we'll end up adding some water and go through the steps to get this material to precipitate. And then finally, we'll have to filter it. Well, it's been a few minutes. Let's see what's happened. Absolutely nothing. That is not a surprise. So we're going to add the procedure calls to add some water to this. And at this point, we're probably going to see some solid. So I don't want to do this. We do have a stir bar in here, so we can stir this, put that stir bar to work and stir it during the addition of water. But I don't want to do it with the ice bath here, because we can't see with the ice bath. So let's just take this off the ice for a moment. Open it up. I know it's all fogged up. Let's fix that if we can. Okay, there we go. Now we can see kind of. And I'm going to add about 3 milliliters of water. We have about 3 milliliters of ethanol. I think I added a little bit more, but about 3. So we're going to add water in here as it stirs. And as soon as I can see some clear solid, it's looking like solid. Okay, let's hold this up now. Now, I'm not sure if you can see, but that's definitely got some cloudiness to it. That is some precipitate, and we've really added very little water. So let's drop-wise add this. Whenever you're mixing solutions, it's good to add them with some mixing. Don't just slop all the water in there at once. Let it all kind of go in slowly. Okay. Okay, that looks good. So, now I've taken this off the ice. We want to put this back on the ice. Let's bring our ice bath back up. We'll put that back in. There's still a little hole in the ice. And I have, this is about a 50-50 mix. This is maybe 20 milliliters of ethanol and water. And I just want to get that chilling. We are going to do a filtration of this mixture, and we're going to need some rinse solvent. And ideally, your rinse solvent should match whatever the liquid is in our vial. And that's about 50-50 ethanol water. This should be about 50-50 ethanol water, and it should also be cold. So we'll get that chilling so it's ready for when we need to do the filtration. Well, we are ready to do a filtration. So we have our product. It's nice and cold, and it's filtered, and it's nice and thick with precipitate, so that's good. We have our cold rinse solvent. That's about 1-to-1 ethanol water. And now we have our filtration set up, our Buchner funnel and a sidearm flask. And we can take a peek in here and make sure the filter paper is covering up all those holes, and it is. So with that, I'm going to turn on our house vac, and let's seat the paper. We're going to seat the paper with the same solution that we're using for the rinse. It's approximately the same that's in this little vial. And I'm going to swirl this around. I do have a stir bar in here. I'm not going to worry about the stir bar. If it falls in, I can get that back out later. I don't think it did fall in. No, it didn't. Okay, so you hold down the funnel. Make sure you have a good seal. Now, get some of our rinse solvent. And mix that around. Good, good. And I said I'm not going to worry about the stir bar. You know what? I'll go. I'm not, since I haven't done it. Whoa, oh boy. That, you know, things float in water. Sometimes you forget. Things will float in water. Let's just do one more rinse. Since I haven't gotten the stir bar in there yet, I'm going to be careful and pour it a little more slowly. There we go. And the stir bar is still in the vial. That's good. Not a big deal if it falls in. Okay, so let's use our pipette and get just a little bit more water. Rinse that in there. We want to rinse it, but we don't want to overdo it, because at all that rinse solution that we put through there, we're potentially dissolving some of that product. So this is almost finished. Drawing through. Of course, you can watch it drip. I'm watching from the top of the funnel. And if we take a peek in here, there's not really much liquid in there. You can see where the solid has kind of piled up around the holes in the plate underneath the filter paper. Okay, that's it. So we filtered our product. Now we need to let this dry. I'm going to let this stand on this sidearm flask for a little bit. And then we'll put it out on a weighing paper, and we'll see how much solid we collected. Here is the final product. It was scraped off of the filter paper and out of the Buchner funnel. That compound in the middle of that weighing paper has a mass of 334 milligrams and is a very pretty white solid. Of course, the appearance of a product is not the same as gathering characterization data as evidence of purity and structure. We need to look at some data before being too confident on the success of this reaction. Let's begin with the TLC and melting point data. On the screen, we have the TLC of our product. This TLC shows 3 lanes. Each is the same, but the concentration differs, with the right lane being the most concentrated. Under UV light, this looks like one spot in each lane. I admit that the most concentrated lane looks like it has a smudge or streak. It's hard to see clearly in this picture, but this region here is clearly not clean when the plate is viewed in person. This streakiness could be an artifact of the higher concentration in this lane. It could be an impurity. It could be some random dirt on the plate. The other 2 lanes, however, look perfect. So I'm going to assume this is one spot, but we'll need to be sensitive to additional evidence of low purity in the product. The RF value for the spot is 0.26, and the mobile phase was 50% ethyl acetate and 50% hexane. The observed melting point was 191.9 to 193.1 degrees Celsius. The literature melting point reported in the reference on the experiment slide was 194 to 195. So we have a sharp melting point close to the literature value. I'm now more inclined to believe that the product is clean. Things are looking good. How about the NMR? Here is the full NMR spectrum with the structure of our IMIDE product. Everything looks okay, but we need to zoom into different regions to understand whether the signals in the spectrum are consistent with our product. This is just the upfield region of the spectrum. Let's work from right to left. These signals at around 0 and 1 ppm are from the cyclopropane part of the molecule. The two CH2 hydrogens are not magnetically equivalent and show up separately. Here and here, 1 hydrogen each. The two remaining CHs overlap because of symmetry in the structure and appear at about 1.2 ppm, 2 hydrogens based on the integration. I will note that the two signals around 0 ppm are kind of lumpy. In the anhydride starting material, these signals are much sharper and resemble quartets. In this structure, almost no coupling is visible. These peaks look like broad lumps. That's surprising, and we'll be able to explain these broad signals once we finish analyzing the spectrum. I do still want to make a comment about the lack of shape of these peaks at this time. Further downfield, at about 2.5 ppm, we have our residual DMSO signal from our NMR solvent. We do not need to interpret this signal. Continuing past 3 ppm, we have a cluster of peaks with an integration between 8 and 9 hydrogens. If we look at our structure, we should have only 4 hydrogens in this region. The 2 hydrogens next to the carbonyls and the 2, it's hard to fit here, the 2 bridgehead hydrogens. Why do we have 8 or more based on the integration? The issue is the NMR solvent. DMSO generally contains water, and water shows up close to 3.5 ppm in DMSO. My best guess is that this tall peak is from water, and the remaining signals, hopefully with an integration close to 4, are from our other upfield peaks. I sort of made excuses for some of the upfield peaks. How about the downfield peaks? Close to 6 ppm, we have the 2 alkene hydrogens. They look good. Continuing downfield, we have 2 separate signals for the hydrogens on the aromatic ring. Each pair of hydrogens shows up as separate 2H signals for a total of 4 hydrogens. That looks nice. Last we have the NH. Amide NH groups appear very downfield. This signal, actually 2 signals, is a bit odd. It's not a 1 hydrogen signal, but 2 signals that collectively add up to 1 hydrogen. What is happening here? Well, this compound, which is after all an active ingredient in a pharmaceutical drug, is a very well characterized compound and is known to exist as an equilibrium of 2 relatively stable conformational isomers. The isomers involve the rotation about the amide CN bond. These isomers are called rotational isomers, which is sometimes shortened to rotamers. So I'm explaining these 2 peaks by saying we have 2 isomers. There is another possibility. Maybe one of these peaks is from the NH of our product, and maybe the other peak is an impurity. That is completely possible. I have 2 reasons I believe these peaks are from 2 conformational isomers. First, this is a known compound in the literature, and the presence of rotational isomers by NMR in DMSO as a solvent has been reported in the literature. That's a pretty good reason. My second reason is that the 2 peaks both have an integration less than 1, and they collectively add up to about 1. So the integration for these 2 signals adds up to 1 and is consistent with the idea we are seeing 2 different signals based on 2 different conformations. If the integration for one peak was 1H and the other was 0.5H, then it would be more likely that the 1H peak is from our compound and the 0.5H peak is an impurity. Let's talk more about these rotational isomers. Here is a zoomed-in view of the two signals. To the left is a depiction of both rotamers. Because of resonance, the CN bond has hindered rotation, and interconversion between these two forms is slow. In fact, it is slow enough that the NMR can capture the presence of the two forms. Note that almost all molecules exist in equilibrium with multiple conformations, but the conformations interconvert so quickly relative to the timescale of running an NMR scan that the spectrum shows an average of all the signals together. In theory, if we heated this sample while acquiring the NMR spectrum, and that is possible, then we could make the interconversion of the rotamers fast, and these NH signals would coalesce into a single peak with an integration of approximately 1H. There are consequences of seeing two rotational isomers. Yes, we can distinguish the different NH signals, but the CH signals of the rotamers, while different, mostly overlap in the rest of the spectrum. That leads to rounding of the CH signals throughout the spectrum, and they end up looking like broad lumps. That's the reason I believe the other signals in the NMR do not show clear multiplicity patterns. That's enough about rotamers. Hopefully, after looking at the TLC, melting point, and NMR spectra, you feel comfortable that the compound is of high purity and the correct structure. Here is the reaction again. Let's identify the limiting reagent so we can calculate the yield. For the anhydride, we used 196 milligrams. The molecular weight is 190.20 grams per mole, so we used 1.03 millimoles of the anhydride. For the hydrazide, we used 198 milligrams based on a molecular weight of 204.15 grams per mole. We used 0.970 millimoles of the hydrazide. Since these reagents react in a 1-to-1 ratio, we will run out of the hydrazide first, and the hydrazide is the limiting reagent. Therefore, 0.970 millimoles is our theoretical yield. What did we obtain from the reaction? We obtained 334 milligrams. The product has a molecular weight of 376.33 grams per mole, so we obtained 0.888 millimoles. That is the actual yield. Our percent yield is actual over theoretical times 100. That is 92%. A 92% yield. I have run this reaction 3 times. Once I spilled the reaction before I isolated the product, so that data point isn't valid. The other time I got a 77% yield. Here we have a 92%. The literature yield is 87%, so this is indeed a reproducible, high-yielding reaction. So this reaction is a very nice demonstration of converting a cyclic anhydride to an imide. I have mentioned a couple times in this video that this product is called tecovirimat, the active ingredient for TPOXX, a drug for smallpox patients. At the time of this video, TPOXX has been discussed as a potential treatment for monkeypox patients, but TPOXX does not have regulatory approval for use against monkeypox. Any use of TPOXX in monkeypox patients would be considered an off-label use of TPOXX. Finally, I want to be very clear that this video does not describe a synthesis of TPOXX. TPOXX is a drug product that includes not only tecovirimat, but also formulation ingredients, excipients, to ensure stability and safe, effective delivery of tecovirimat to patients. Furthermore, active pharmaceutical ingredients, like tecovirimat, that are used by patients must be prepared and handled according to protocols called Good Manufacturing Practice, or GMP. This laboratory experiment is an educational exercise only and in no way conforms to GMP and does not afford material that is safe for use in patients. I hope you enjoyed this reaction, which involves the conversion of a cyclic anhydride into a cyclic imide, and is also an API in an approved drug. If you are interested, handouts for the procedure are linked through the video description. Please subscribe, like, or leave a comment. Take care.